Hello viewers, we are now taking you through the story for A-Level Physics Paper 1. And in this video, we're going to go through the marking guide of Senior 5 of Physics Paper 1 for mid of Term 2 for the year 2023. And this video is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So like I already told you, in this month of July, we are interested in uploading marking guides for mid-of-term exams, mock exams, and also UNEB exams for physics and math. So what is ticked is what you have uploaded so far. Math 1 mod was uploaded, Math 2 mod was uploaded, Sub-Math mod was uploaded, and now we are going to look at Physics Paper 1 of Mod 2 for the year 2023. So shall keep uploading video by video until all these exams are done. Then we shall go back to our normal notes. So for those interested in buying resource books, the resources or the books we recommend for A-Level are strictly these ones. So Math 1, there is this. Actually, in Principal Math, there are 4 books which you need to buy. So there is Math 1 notes, Math 2 notes, Topical Question Bank, and Termly past papers. So Sub-Math is only 1 book, and Physics there are also 4. There is Physics 1 notes, Physics 2 notes, Topical Question Bank, and its solutions. So you can contact the author on this contact or send a WhatsApp message for copies of these books. But I highly recommend that you get these books. So where necessary, these are the constants we shall be using. So acceleration due to gravity in physics, it is 9.81. Density of water is 1,000 kilograms per meter cubed. Electronic charge is 1.6 exponent negative 19 coulomb. Stefan's constant is 5.7 exponent negative 8 watts per square meter per Kelvin to power 4. Speed of light in vacuum is 3 exponent 8 meters per second. Universal gas constant is 8.314 joules per mole per Kelvin. Specific heat capacity of water 4.2 exponent 3 joules per kilogram per Kelvin. And specific heat capacity of copper 400 joules per kilogram per Kelvin. So where necessary, these constants can be used along the way. We shall start with question 1. Question 1 part A, Roman 1 says, what is meant by dimensions of a physical quantity? So dimensions of a physical quantity is the way that given quantity is related to the basic or fundamental quantities of mass, length, and time. So you can use the word basic or the word fundamental, and these are the quantities we're interested in. So there is mass, length, and time. Then Roman 2 says, according to Pascal's equation, the volume flow per second, V, of an incompressible liquid of viscosity, equation of viscosity that, flowing through a tube of uniform internal radius R and length L under a pressure difference P1 minus P2 between its end is given by this expression. Show that the equation is dimensionally correct. So here I think we realize that we missed a pi in the question. This pi has to be there. In this question, a pi was left out, but it was an error, so it has to be there because that's what makes the equation correct. this Pasolini's equation. So from that equation, so for this solution, if you work out without this pi, it is still okay, but I just put it there for you to realize that a correct equation has to have pi. So dimensionally correct means dimensions on the left hand side are equal to dimensions on the right hand side. So I'll get the dimension of V. I think you see this box bracket. When you put a box bracket, it means you want to get the dimension of what is inside the box bracket. Dimension of that, dimension of that, dimension of that, pressure difference, dimension of this constant, of this question of viscosity, length, and this 8. Now, when you remove the box bracket, it means you have already got the dimension. For example, if you look at this, here there was a box bracket, but here there is no box bracket. So if by mistake I put a box bracket here, you'll get no mark, because a box bracket means you want to get the dimension of what is inside that box bracket. So dimension of V is this, because it was volume per second. Volume is L cubed, per second is T to the power negative 1. Dimension of a constant is 1. Dimension of R is length, but there's a power 4. Dimension of pressure difference, so pressure is M L to the power negative 1, T to the power negative 2. Then dimension of 8 is a constant, so you put 1. Coefficient of viscosity, it is known, and length is that. So after getting the dimension, next is to use the rules of indices to simplify. So when you simplify, how does this come about? First of all, there is this L to the power negative 1 and this L to the power negative 1. So it cancels. Then we have L to the power 1 and L to the power 4. So the power reduces by 1 to become 3. That is why you see L cubed. Okay. Then this M goes with this M. Okay. Then this T to the power negative 1. Here there is T to the power negative 1 and here there is T to the power negative 2. So same base, you subtract the powers. So negative 2 minus negative 1 gives you negative 1. That's why you see here T to the power negative 1. Now we realize that left hand side is equal to right hand side. And when that is done, we can now conclude that the equation is dimensionally consistent. So 1 mark for the definition, 1 mark for this, 1 mark for this dimension. For each dimension had a half a mark. Each dimension had half a mark, and this conclusion. That was part A. Now we shall go to part B. So B Roman 1 says define a unit of measurement. So a unit of measurement is a definite magnitude of a quantity that is used as a standard of measurement. So the key word is this word standard. Standard of measurement of the same kind of quantity. So don't forget this word standard for measurement. That was Roman 1. Then what about Roman 2? Roman 2 says the period capital T of a pendulum of mass m is given by the expression this: T is equal to 2 pi square root of L over capital mgh, where g is the gravitational field strength. Okay, I know by now you have not yet covered gravitational field strength, because it is easily understood under the topic of gravitation. But the good thing is that they gave us something in bracket. Do you see this bracket? It means that gravitational field strength is the same as force over mass. So this will be the hint to help us get the dimension of G. Okay, and H is the length. Good enough, we know the dimension of length. determine the base unit of the quantity L. So base unit means it has to contain the fundamental units of the fundamental quantities. Remember, units of fundamental quantities, there is mass. We have mass, which is kilogram. We have length, which is meters, and t, which is seconds, time, which is seconds. So this base unit they want it in the form of kilogram, meters, and seconds. So don't again change it to make, for example, newtons. No, we don't need joules. Those ones we don't need them because they said base unit. So it has to have these three, and don't simplify them. Okay, so let's see that part. So that is the equation they gave us. We have to look for a way of making L the subject. First thing is to square both sides to come up with this. So t becomes t squared, this becomes 4 pi squared, and then the square root, so if the square root goes away, remain with L over mdh. Now from there I can make L the subject. I'm going to take the whole of this side to give me this. Then this one also goes this side to become a denominator. Now that I've managed to make L the subject, next is to get its dimension. And from the dimension, we shall be able to get the base units. So the dimension of L is equal to dimension of this t, dimension of this m, dimension of this g. This g is no longer acceleration due to gravity. Remember, under the table of constants, we denoted acceleration due to gravity as g, but now this g in this question, it's called gravitational field strength. And we have to use the hint given that gravitational field strength is force over mass. M and constant. So dimension of t is still t, and there's a square. Capital M, the dimension is m. The dimension of gravitational field strength is force over mass, and h is capital L. Then the whole of this is a constant, that's why you put 1. Now next is to simplify. How did they get ml squared? So let's see how it came about. 1, this m and this m can cancel. Okay, then there's something funny between this t and this t. They have the same base, so you add the powers because it's multiplication. So when I add the -2 plus 2, I get a power of 0. And we know that any number to power 0 is 1. That is why there is no t here. Okay, what about L? L, there is this and this. So multiply the two to get L squared. Then when you realize m, there is only one m, which is here. So that's how we got ml squared. And after getting its dimension, we can now get the base unit, because m denotes kilograms and L denotes meters. So that is how the 4 marks will be got. So each dimension is half a mark. Each dimension seen is half a mark, and the output also has a mark. Now we shall go to part C. Part C, Roman 1 says, then we are now on part C. C Roman 1 says, distinguish between vector and scalar quantities. So a vector quantity is a physical quantity which has both magnitude and direction, while a scalar quantity is a physical quantity which has only magnitude. So vector has both magnitude and direction, while scalar has only magnitude. That was Roman 1. Then Roman 2. Roman 2 says, given the quantities thrust is force, another word to mean force, atmospheric pressure, temperature, and momentum. Group the given quantities above into vector and scalar quantities. So you have to identify of these ones, which ones are scalar and which ones are vector. So vector quantities, there is thrust and momentum. Scalar quantities, we have atmospheric pressure and temperature. And that's what they wanted. Then part D. Part D says, what is meant by resolution of a vector? So resolution of a vector is the process of splitting up a vector into two or more components stroke parts such that the sum of these components gives the original vector. Most students stop at this part, splitting up a vector into two or more components, and they stop there. But that is not a complete definition. You have to conclude. You have to complete and say that the sum of these components must be equal to the original vector. So the other part is needed. Most students were stopping at this part and they couldn't get that one mark. So that's how the mark awarding was done. So now we shall go to part E. Part E says, the figure above shows a body of mass 2 kilograms acted upon by forces of magnitudes 5 newtons, 5, 6, and 8. Then they said, calculate, Roman 1, the resultant force on the body, and Roman 2, the distance covered by the body in 2 seconds, given that it was initially at rest. So in other words, they want you to resolve these ones, and after that you get the resultant. So what you are going to do, we are going to first redraw the diagram for us to easily resolve. So you come and put the 5 Newton, the 6 Newton, the 5 Newton here, and the 8 Newton. So I think realize something, that the first thing to do is to get angles to the horizontal. Angles to the horizontal. Angles to the horizontal. That should be the first thing to do before you resolve. Then after getting angles to the horizontal, then you remember that always horizontal component will have cos, while the vertical component will have sine. You can see it here, cos, 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 sine, sine, sine. Okay. Now next is to find out how do you determine these negatives. So those negatives are got from this sign convention. We call it a sign convention, that vectors to the right are positive, while those to the left are negative. Vectors upward are positive, while those downwards are negative. Okay. Now let's start with this 5 Newton force. This 5 Newton force is entirely horizontal. That is why you put a horizontal 5, the whole of 5 here, and there is no vertical component. That's why you put 0 for vertical component. Okay. Then the 6 Newton can, to move from start to end, you move from here horizontally, you move to the right, which is positive. And then you go upward, which is also positive. That is why you see both are positive, horizontal and vertical. Then for this 5, horizontally you move to the left, which is negative, and then upward, which is positive. That is why you see a negative here and a positive here. Then this 8, horizontally you move to the left, which is negative, and also downward, which is negative. That is why you see negative here and negative here. So basically that is how they resolve. You remember to put the signs, positives and negatives. Otherwise the resolving will not be okay. Now we are going to combine them to get the resultant. So this will be the resultant but in vector form. Yet the question wants the resultant in form of magnitude and direction. So what you're going to do, we are going to draw a right angled triangle, where this is the positive horizontal will be to the right, then the vertical is also positive, meaning it will be upward. Then from a line from start to end will give us the resultant. And this resultant, its magnitude is what we got here. This squared plus this squared. Square everything under square root to give you 3. But we need magnitude and direction because force is a vector quantity. So what you're going to do, we are going to use SOHCAHTOA to get this angle. This is opposite, this is adjacent, meaning we shall use tan. And then we have theta as 60 degrees. Then we shall conclude the resultant force is 3 in the direction 16 degrees above the positive horizontal. And basically that's how the marks will be awarded. Half a mark for all the horizontal component and half a mark for the vertical component. Then substitution here, output, ratio, conclusion. That was E Roman 1. What about E Roman 2? E Roman 2 says that calculate the distance covered by the body in 2 seconds given that it was initially at rest. So we know the initial velocity, we know the time, and acceleration can be got from the resultant because we know that F is equal to ma. So I'll come here and remember that my resultant force is 3. Therefore, F equal to ma, substitute for F and m to get A, which is 1.5. Now that I have acceleration, I can use the second equation of motion. So initial velocity is 0, time is 2, acceleration you have got as 1.5, and time is 2 to give you the distance required as 3 meters. That was question 1. Now we shall go to question 2. Question 2 says, part A, what is meant by the phrase velocity of A relative to B? So the phrase velocity of A relative to B is used to mean the velocity with which a body A moves as observed from another body B. So the observer is B and is observing the velocity of A, but they're both moving. That's what they mean by A relative to B. Velocity of A as it appears to the observer B, or velocity of A as seen by the observer B. Any is okay. That was part A. What about B Roman 1? B Roman 1 says, ship A streams northwest at 60 kilometers per hour, whereas ship B streams southwards at 50 kilometers per hour. Initially, ship B was 800 meters due north of A. Find Roman 1 the velocity of A relative to B, and Roman 2 the shortest distance between A and B, and Roman 3 the time taken for the shortest distance to be covered. Now this question can be done in 2 ways. One can choose to use geometry, another one chooses to use vector, or you can choose to use a mixture of both geometry and vector. So for me, I'll choose to use a mixture of both geometry and vector. So the first thing to do is to state to first sketch the individual direction so that you can transfer them into vector, because here we are given direction and magnitude. You have to change it in vector. So northwest is ship A, the velocity is 60 kilometers per hour, direction is northwest. So I'll come here and so that where is my compass direction and where is northwest? Northwest is that. Okay, what about the second one? The second one is velocity is 50 kilometers per hour and direction is southwards. So we'll come here and also draw it. That sketch helps us to get the vector or the geometry, but for me I'll use vector. So in vector form, velocity of A will be that, got by resolving. Resolve to the horizontal and also to the vertical. Horizontal is to the left, which is negative. Vertical is upwards, which is positive. This one, it is entirely vertical, meaning horizontal is 0, then vertical is negative because it is downward. After converting them in vector form, you shall remember the formula for relative velocity. That velocity of A relative to B is equal to velocity of A minus velocity of B. So substitute for VA and for VB and use the calculator to get the output to 4 decimal places. But remember, I want the answer in magnitude and direction form. So I'll come and say that the magnitude is that, square root of this squared plus this squared to give you that. What about the direction? Direction, I'll make a sketch. Remember, horizontal is negative, but vertical is positive, so it will be upward. Then line from start to end gives the relative velocity. So they want the direction from north towards west, therefore, which is, let me call it theta, and by this theta is equal to this, alternating angles. Then I'll remember SOHCAHTOA and I'll use tan, where theta will be that. Therefore, I can state that the direction is north, 24.66 degrees west. So angles are to 2 decimal places, and that's what they wanted. So have a mark for this, have a mark for this, have a mark for substitution, output, division, and stating the direction. That was part B, Roman 1. What about B, Roman 2? B, Roman 2 says, find the shortest distance between A and B. So shortest distance, there I'm going to use geometry. Like I told you, there are 3 ways. You can either choose to use vectors alone, or geometries alone, or a mixture. So what I've done, part A I've used vector, now part B let me also use geometry. So geometry, you have to state the initial positions of A and B. And they told us ship B initially was 800 meters due north of A. So I'll come and locate ship B. It is north of A. A is here, then north is here. I'm changing to kilometers because my velocity, if we go here, the velocity was in kilometers per hour, meaning it is up to you to choose whether to change the velocity to meters per second or you change the distance to kilometers. So I realized that changing the distance is easier, but either way is okay. So from there, I'll come and draw my relative path. I think we saw here, if you look at this, we realize that the relative velocity is in this direction. Do you see that? And this angle is 24.66. So I'll come and draw my relative velocity or relative path. When you draw the relative path, then you drop a perpendicular from B to meet this relative path. So when you draw a perpendicular, it will be in that form. And this distance BC is what we call the mean shortest distance between A and B. So a good thing I know this angle and I know this hypotenuse, so I can get this opposite. So opposite and hypotenuse are related by sine from our SOHCAHTOA. So that's what I can use. So they told us to get both distance and time. Let me first say it here. Shortest distance between A and B and also time taken. So any of the tools here, you chose to begin with this Roman of shortest time. So shortest time, it means distance SC divided by the relative velocity. So distance SC is that, relative velocity is that, to give you that in hours. Then one can choose to convert to seconds. It is still okay. Then for the shortest distance, I want D minimum, which is BC, and to be 800 sine 24.66 degrees. And that will be the distance. So it is still okay to put this distance in kilometers, and also it's still okay to give this time in seconds. But if someone left it in hours, it's also okay. So that's how the marks would be awarded. Now that was part B. Now we shall go to part C. So part C, Roman 1 says, what is a projectile? So a projectile is a particle which, when given an initial velocity, can be left to move on its own in air in presence of a constant force field. That's what they mean by projectile. Then Roman 2, an object is projected from a level ground with an initial velocity u at an angle beta to the horizontal. Show that the maximum height h max attained by the projectile is given by this, where g is the acceleration due to gravity. So we know that at maximum height, vertical component, it is vertical component strictly, which is equal to 0. So the vertical component of velocity is 0. So I'll come and say that Vy squared is equal to u. This is equal to, this is Vx. No, remember we're dealing with vertical. So this was supposed to be Uy, like that. Uy squared minus 2gs. Then I come and substitute for Vy is that, then Uy is u sine beta. Then it is squared minus 2gs. Then I remember that when V is 0, S is h max. Okay, then from there I realized that I can make h max the subject. And that's what they wanted. That was Roman 2. What about Roman 3? Roman 3 says, if the velocity in C Roman 2 is 23.5 meters per second and h max is 13.5 meters, deduce the angle with which the object was projected. So I'll come and quote what I proved, then I'll substitute for h max and for u and for g, which is in the table of constants, and remain with beta as the only unknown. So my aim is to make it the subject. So sine beta is that, arc sine will give you 43.83 as the angle, and that's what they wanted. So now shall go to part D. Part D says a bomb is dropped from an aeroplane when it is directly above the target of height 1402.5 meters. The aeroplane is moving horizontally with a speed of 500 kilometers per hour. Determine where the bomb will hit the target. So shall make a sketch of the aeroplane and the target. So that's the aeroplane and the target is vertically below it at a height of 1402.5 meters. And it is moving with a horizontal velocity of 500 meters per second. So when it is dropped, it will make a projectile and hit at this point. So it is x meters from the target, but what is that value of x? So you first consider vertical motion where y is equal to u t. So remember, it's entirely horizontal, meaning the vertical component is 0. That's why you see this 0. Plus a half gt squared. Then you come and substitute for y, for g, and get the value of t. After that, we shall now consider horizontal motion, where x, we shall first change, because this time is seconds and this was kilometers per hour, so we convert to meters per second. Then we substitute that x is ut, where u is that and t is that. Then you get the value of x. So I can now conclude that the bomb won't hit the target because it is off target by this distance. And that's what they wanted. So now shall go to question 3. Question 3 part A says define specific heat capacity. So specific heat capacity of a substance is the quantity of heat required to raise the temperature of 1 kilogram. So when you see this word specific, the word 1 kilogram must be seen. 1 kilogram mass of a substance by 1 Kelvin. That was part A. Then part B, describe, stating the assumptions made, an electrical method for the determination of the specific heat capacity of metal. So metal is a good conductor of heat. So you come and make an illustration. So that is the metal being lugged. So that is the metal being lugged by an insulation. Then from there, you are going to drill 2 holes. Then one hole will have a thermometer to measure the temperature, and another hole will have the heater. So you shall connect a heater to a circuit or a power supply. Okay, so that is the circuit diagram we're going to use. Now let's see how that diagram works. Shall come and say that 2 holes are drilled in a metal block and its mass m measured and recorded. I think you saw the 2 holes. Then a thermometer is inserted in one of the holes and an electric heater in the other. I think we also saw that. Then the holes are filled with a conducting fluid and the apparatus is insulated. The reason for this is to prevent heat loss. When that is done, the initial temperature θ1 is recorded. And after recording it, you switch on the heater and also start the stop clock simultaneously. Simultaneously means they all start at the same time. When you are switching on the heater, you also start the stop clock at the same time. So when that is done, the voltmeter and ammeter readings V and I respectively are noted. So voltmeter reading V and ammeter reading I are noted. So after some time, there will be a considerable rise of temperature, and that is when the heater is switched off and the stop clock stopped, both at the same time. So the highest observed temperature, θ2, of the block is read and noted, and the time t for which the heater was on is noted. So from that, the specific capacity of the block, which is the metal, is now calculated from the formula that C, which is the specific capacity, is equal to IVT divided by M in brackets changing temperature. And basically that's what they wanted. But they also told us, if you read the question, there's something they told us. They said stating the assumptions made. So we need to state the assumptions. So 1, it is assumed that heat lost to the surrounding is negligible. Then 2, it's assumed that the quantity of heat gained by the thermometer and the heater is negligible. And 3, it is assumed that the volume of the solid, which is the metal, is constant. Hence, there is no work done against atmospheric pressure. I think you very well know that metals expand when heated. So here it is assumed that the volume remains constant, in other words, it doesn't expand. Then part C, that was part B, now part C. Part C says, in an experiment to determine the specific heat capacity of a liquid using the continuous flow calorimeter, the readings are taken when the apparatus is attained. When the apparatus has attained a steady state. Explain the meaning of steady state. So in other words, what does the word steady state mean? So steady state is a condition when the inflow and outflow temperatures are constant and heat is lost to the surrounding at a constant rate. So that's what they mean by steady state. There was part C. What about part D? Part D says, when water is passed through a continuous flow calorimeter at a rate of 100 grams per minute, the temperature rises from 16 degrees Celsius to 20 degrees Celsius. When the PD across the heater is this and the current is this, so this temperature rise is when the V is this and I is that. Okay. When another liquid at 16 degrees Celsius is passed through the calorimeter at a rate of 120 grams per minute, the same temperature change is obtained when V is that and I is that. Calculate the specific heat capacity of the liquid. So shall first let C2 be the specific capacity of the liquid and H, capital H, be the rate of loss of heat to the surrounding. So you have to get the mass per second. So mass per second will be, you remember it was 100 grams per minute. So I have to change to kilograms per second, which is that for water. Then for the liquid, 120 grams per minute is converted to kilograms per second, which gives you that. Then by conservation of energy, heat lost is equal to heat gained, or heat given out is equal to heat gained. So this is heat given out generated by the heater, and this is the heat gained by the liquid, and this is the heat lost to the surrounding. This is for water experiment, and this is for the liquid experiment. So these two, remember our aim is to get C2, so we have to eliminate H by subtracting the two equations and make C2 the subject. So when I do that, I'll come up with this. Then I'll substitute for I1 is here, V1 is there, I2 is there, V2 is there, M1 is there, C1 is there, change in temperature is that, M2 is there, C2 is what they want, change in temperature is that. My aim now is to look for a way of making this the subject. So I use the calculator, the whole of this gives me this, then the whole of this bracket gives me this, and the whole of this gives me that. Then take this one this side, and this one comes this side to give you this, and then makes it to the subject. And that's what they wanted. Then part E says define latent heat. So latent heat is the quantity of heat required to change the state of a substance to another state at the same temperature. So the keyword is the word same temperature. I think realize here there is nothing like specific. If there was a word specific, we would use 1 kilogram. But with here they just said latent heat, so you just use any mass. That was E Roman 1. What about E Roman 2? E Roman 2 says, in an experiment to determine the specific latent heat of fusion of ice, a heating coil is placed in a filter funnel and surrounded by lumps of ice. The following 2 sets of readings were obtained. Calculate the specific latent heat of fusion of ice. So Jacquard says that let L be the specific latent heat of fusion of ice and small h be energy gained by ice from the surrounding. So by conservation of energy, electrical energy supplied plus energy gained from surrounding is equal to energy used to melt the ice. So this one is IVT, then this is H, and this is ML. That is for the first set. So in this case, I1, V1 are these ones in the question, this first set. So this is V1, this is I1, and this is M1. But remember it is in grams per second, okay? Then this is V2, I2, M2 in grams per second. Not 1 second, it is grams collected in 500 seconds. So T is 500. So that is the second set. Then I'll eliminate small h and remain with that. Then I'll substitute I2 V2 and the time which is 500 seconds, I1, V1 and the time which is 500 seconds. Then mass, remember mass was in grams, so you change it to kilograms. Also this one changed to kilograms. So now is to look for a way of making L the subject. So the whole of this gives me this, and the whole of this bracket gives me that. There is this L. So make L the subject to come up with that. And that's what they wanted. So that was question 2. Now we shall go to question 4. A Roman 1 says, define specific latent heat of fusion of ice. So specific latent heat of fusion is the quantity of heat required to change 1 kilogram. So because there's this word specific, I think remember in question 3 they just said latent heat, so we didn't mind the mass used. But when they say specific, then the mass should be strictly 1 kilogram, okay, of a substance from solid state to liquid state without change in temperature. That was Roman 1. The Roman 2, state the effect of impurities on melting point. So they only told you to state. I think we even see at the mark, it is 1 mark. So just say impurities lower the melting point. Full stop. That was part A. What about part B? Part B says, Roman 1, explain how a thermocouple is used to measure temperature on a Celsius scale. So first of all, when it comes to a thermocouple, the thermometric property is EMF of a thermocouple. Then from there we shall start our experiment setup that the cold junction of the thermocouple is maintained at ice point. So the thermocouple has 2 junctions, cold junction and a hot junction. So the values of the EMF of the thermocouple, E100 and E0 at steam and ice point respectively, when the hot junction is placed in steam and in ice respectively are noted. So that means that you maintain, like I told you, there are 2 junctions. So maintain 1 at ice. Then this hot junction is put first of all in steam, and you get this E100. Then this one again, put it in ice, you get this E0. That's what their statement means. Then the hot junction is then brought in contact with an unknown temperature theta, and the value of the EMF E theta is noted. Okay. After that, the unknown temperature can now be calculated from the expression that theta is equal to E theta minus E0 over E100 minus E0, everything multiplied by 100. So that was B Roman 1. Now what about B Roman 2? B Roman 2 says, state 2 advantages of a thermocouple. So 1, it can measure temperature at a point. Then 2, it's very sensitive to temperature changes. 3, it is portable. And 4, it has a wide range of temperatures. So basically that's what they wanted in part B. What about part C? Part C says, with the aid of a diagram, describe the continuous flow method of measuring the specific heat capacity of a liquid. So we shall need to draw a diagram. So let's first draw the diagram. So we have a constant water supply, which is this. So it is connected to, so that water supplied passes through a heater. And within that heater there's a vacuum. So that is the temperature, measuring the inflow temperature. I think you remember this is where I talked about steady state. Steady state means inflow and outflow temperatures are constant. So this measures the inflow temperature and this one measures the outflow temperature. And this is the heater. Then this is the vacuum. That heater has to be connected to a power supply, which is that. So this is the source of the liquid whose specific heat capacity is needed. So liquid flows in that form, it is heated, then it goes out to be collected in this container. So there is a constant head supply, then there is vacuum, there is a heater, there is a beaker to collect the water or to collect the liquid. Okay, now let's see how that setup works. One, the setup is as shown above. So this statement is what connects what you're going to write to what you have already drawn. It is necessary. Then the liquid is allowed to flow at a constant rate from the overhead tank. This is the overhead tank, so it flows at a constant rate. The heater heats the liquid until the temp thermometers θ1 and θ2 indicate steady temperatures. So that's what they mean by steady state. So this temp thermometer and this thermometer must indicate constant temperatures. Some students confuse them by saying indicating same temperatures. No, they don't indicate temperature. For example, if this indicates 20 and you say they indicate some temperatures, it means that even this one should indicate 20 degrees Celsius. But that's not what they mean. What they mean by steady state, as this liquid flows, okay, this temp thermometer, the reading keeps on fluctuating, but a point will reach when the reading is steady, let's say 30. Even this one, after being heated, the readings keep on fluctuating, but a point will be reached when the reading is constant, let's say 60. So that's what they mean by steady state, constant reading of thermometer. So inflow temperature θ1 and outflow temperature θ2 are recorded. Then the ammeter reading I1 and voltmeter reading V1 are also read and noted. So this is the ammeter reading and this will be the voltmeter to measure the voltmeter reading, to measure the voltage. So the mass M1 collected, which flows per second, is determined. So what you do, you collect this mass and also read the time it took to get that, to collect that liquid. Then you divide mass over time to get the mass per second. That's what they call M1, mass per second. At steady state, it means that heat generated is equal to heat gained by the liquid plus heat lost to the surrounding. So the rheostat is varied to get a different current and also a different voltage. And because the currents are different, it means that even So the rheostat is adjusted to get a different current to flowing through the circuit until the inflow and outflow temperatures are the same. For example, like we said, if the inflow is 30 and outflow is 60, it means that you again adjust until you and wait until you get 30 here and 60 there. So when that happens, the reading on the ammeter is read and also on the voltmeter is read. The new mass is also measured, mass per second. It is mass per second. So that's how we could get the full mass on this slide, but the experiment is not yet done. We are still continuing. So let's now go to the next slide. Next slide shows that at steady state, I2V2 is equal to, so heat generated is equal to heat gained by the liquid plus heat lost to the surrounding. The reason why we repeat the experiments for the second time is to cater for this rate of heat loss to the surrounding, because we have to subtract the 2 and then deal away with it. So when that is done, you solve these two equations simultaneously and make C the subject. When you make C the subject, this is what you will get. And that is how continuous flow method is used to measure specific heat capacity of a liquid. So that was part C. Now shall go to part D. Part D says a thermometer is constructed with a liquid which expands according to the relation this, where Vt is the volume at T degrees Celsius and V0 is the volume at 0 degrees Celsius. On the scale of a gas thermometer, and alpha and beta are constants. Given that alpha is 1000 beta, what will the liquid thermometer read when the gas thermometer reads 50 degrees Celsius? So first of all, you are given that Vt, you can substitute V100, means where there is T, you put 100. Where there is T, put 100, T, put 100. And they also told us that alpha is equal to 1000 beta. So where there is alpha, put 1000 beta to come up with that. Then V50, where there is T, put 50, 50 to come up with that. Therefore, the unknown temperature which is required will be V50 minus V0 divided by V100 times minus V0, everything multiplied by 100. So substitute for V50, V0 is there. Substitute for V100, V0 is there. Then open brackets. After opening brackets, you realize that this and this can cancel, this and this can cancel, remain with that and this. Then also these two can cancel to remain with this over this times 100, which gives you that as the temperature they wanted. So that was part D. What about part E? Part E says a constant volume thermometer was used to measure temperature when the atmospheric pressure was 760 millimeters of mercury. The following values were obtained. So this is the length of mercury in the closed limb, length of mercury in open limb. So when the bulb is in ice, we have this in closed limb and this in open limb. When bulb is placed in steam, it is 140 millimeters of mercury in closed, 330 in open. When bulb is at room temperature, it is 140 millimeters in mercury in closed and 170 in open. Calculate the room temperature. So there are two alternatives, but let's look at, and we're going to look at each of them. So P, pressure. Remember, constant volume gas thermometer, the thermometric property is pressure. So pressure at 0 degrees Celsius is when bulb is placed in ice, so it is capital H plus H. which is atmospheric pressure plus the difference in the two limbs to give you 750. At 100 still atmospheric pressure plus the difference in two limbs to give you that. Then at unknown temperature or at room temperature, atmospheric pressure, difference in two limbs to give you that. Then when that is done, you can calculate now the temperature from the formula P theta minus P naught over P100 minus P naught multiplied by 100 to give you 20 degrees Celsius. That is one way. Another way you can get the difference in heights in both limbs at 0 degrees Celsius, also the difference at 100 degrees Celsius, and the difference at unknown temperature, at room temperature. Then you code the formula using now, instead of pressure, use that difference in heights. It still gives the same answer. So any of the two is okay. And that's how the 3 marks would be awarded. So that brings us to the end of this video. Thank you for watching, and be reminded the next video will be on Senior 5. This is paper 2 of MOT of term 2 for the year 2023. So if you haven't yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know of any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp so that we can all benefit as a family.